Okay, we can start, and we start by the reminder of some properties of the open Toda chain. So we defined it by Hamiltonian over 2pi square plus some e q I minus q I plus 1 I from 1 to n, I from 1 to n minus 1. So it describes some chain of particles interacting via this exponential potential, and it appeared to be related with some solid physics models, and for us it is interesting because it is integrable. But we only started to discuss integrability property, and the first point in this program was its Lax representation. So first of all, we introduced the Flaška coordinates. AI, which is minus 1 to pi, and bi is 1 over 2 exponential of 1 over 2 qi minus qi plus 1. If you have some problems, it's better to ask and to discuss the definition. It was given last lecture, and we will use it intensively in what follows. So one could describe the the equation of motion in terms of Flaška coordinates. I wrote this last time, but most interesting for us today will be the Poisson structure of our models in terms of Flaška coordinates. So the initial Poisson structure is described by the standard bracket between canonical variables p and q, which is delta ij. And we can extract from this definition the Poisson bracket between Flaška coordinates. It is obviously trivial between coordinates of the same type, bi, bj, but the Poisson brackets between variables of different type are non-trivial. So ai with bi is equal minus 1 over 4 bi, and ai bi minus 1 is equal 1 over 4 bi minus 1. If you have some question, it's better to ask it just now, but it's a straightforward calculation which uses the Leibniz rule and the differentiation of the complex function, the function depending on some function. Okay, to work more systematically with this structure, we introduced the Lax operator, which is a matrix. Those entries depends on the point of our phase space, So it's a matrix of such a kind: B1, B1, A2, B2, B2, etc. AN, Bn minus 1, Bn minus 1. So it's a three-diagonal matrix which is symmetric and which is defined in terms of Flaschke coordinates. And it was a statement, theorem, that the equations of motion of the open Toda chain are equivalent equivalent to the equation, to the matrix equation L dot M of L, there M of L is equal L plus minus L minus, and this L plus and L minus are upper triangular part of the operator IL and the lower triangular part of the operator L. In our case, it is also a three-diagonal matrix, but with zeros on the principal diagonal: B1, Bn minus 1, minus B1, minus Bn minus 1. And the last important statement of the last lecture was the theorem that all spectral invariants of the matrix L are integrals of motion for the Toda chain. Ik, which are traces of Lk, are integrals of motion for the open Toda chain. So in a sense, this is the motivation why we are looking for some exotic representation of our dynamics, but it's a very useful form of representation of the dynamics. So, for example, quite automatically, it doesn't depend on the form of this operator M, but if our dynamics can be put into the form of the Lux representation, so it's the spectral invariants of the Lux matrix are integrals. But at this moment, it does not guarantee the involutivity. So we have constructed a big family of integrals, but it is not evident that they are involutive. First of all, let us discuss its functional independence. Comment. If involutive, does this family is functionally independent? Thus, this family is functionally. Thus, this family functional independent is functionally independent. let us consider such a map. So we have R, in fact, 2n minus 1 in terms of the coordinates A and B. And we can consider just a projection to the space Rn, which is Rn of coordinates A1, An. So we can forget the variables b and consider only functions on variables a. So it is even better to look for the space of polynomials. I'm sorry, polynomials R of a I and b j, and to consider its projection to the space of polynomials only on variables a. It means that for each polynomial which depends on b, so I can describe this map on monomials. There is a monomial. Each monomial is some monomial with multi-index m, b, k, which means that we take a1, m1, a2, m2, an, mn, b1, k1, bn minus 1, kn minus 1. So this map from am bk is equal 0 if k is not 0, and am if k is equal 0. So I prefer to invert the arrow here. So there is some embedding of the smaller space into the bigger space. Like this is R2n minus 1, and this smaller space is Rn. And we can restrict functions. So these are functions on the bigger space, this space of polynomials. It is the space of polynomial functions on the bigger space, and this is the space of function on the smaller space. We can define the restriction of the function on the bigger space to the functions on the smaller space. And this restriction is the linear map, and it acts like this map on monomials. So if a monomial contains some variables depending on b, then its restriction to this subspace which correspond to the values of b equals 0, it produces the zero function. Please understand this map. We will use it strongly in the other constant sign scheme, which is one of the major procedure to obtain integrable systems. So if you have questions about this map, it's a better time to ask them. Okay, if it is clear, I'd like to apply it to the functions ik. I'd like to consider functions ik tilde, which are given by application of this map of this map I of restriction to the initial functions ik, who are the spectral invariants of our Lax operator. So using its geometric interpretation, this map means that we just restrict our functions to the subspace on which the b coordinates are 0. So, and it means that these functions are just spectral invariants of the diagonal matrix, of the matrix with the diagonal A. And that means it is just the Newton polynomial on variables A. So it is the sum over I, power k, which is called the Newton polynomial of order k on A. Very useful polynomial in the theory of functions, of special functions, orthogonal polynomials, and many other subjects. And it is very known that they are independent, but it is even simpler to calculate its Jacobi matrix. Just Lemma. The Newton polynomials n1 of A and n of A. The A is the set of n variables, 1 and are functionally independent. Are functionally independent. So we have to calculate the Jacobi matrix. So d n k over d a I is k a I k minus 1. Okay, so it means that the Jacobi matrix is 1, 1, a1, a n, 2. I'm sorry, I suppose that it is 2, 6 a1 square, 6 a. No, even not 6. It's 3 a n square, etc. So it's proportional to the van der Monde matrix, which is not degenerate. Okay, so the projections of our spectral invariants are independent on a small space. It means that the Jacobian is non-trivial even on the bigger space, because on the bigger space its Jacobian contains additional terms, but even this part is non-degenerate. Okay, please. I think it's a very good technique to work with some special functions. Okay, but so our aim for today is to illustrate its involutivity, and to do this we will consider some additional instrument.
What is fundamentally functionally independent means?
It means that the differential are linearly independent in generic point, or which is equivalent that the Jacobi matrix has a maximal rank.
Okay.
this Jacobi matrix, if you consider Jacobi matrix of the function on the full space, they contain this part and some additional part. But this part is already of the maximal rank, so they're independent on the full space. So our, in fact, local aim is the involutivity of our family of functions. But we will do some exercises on what is called R matrix formalism. So it helps in this local problem, but it is more universal. So it appears in many models, and it is related with such an interesting and important technique as Lie-Poisson groups. Lie-Poisson groups and its quantization, which is called quantum groups. And we will start by a very simple exercise, but I need some technicalities. So I will consider the Lax matrix for the Lie algebra J-Len. Lax matrix. It is the following object. It is L, which is a matrix L n by n. Those elements are generators of the Lie algebra J-Len. I will write it in the following way: Eij. The sum is over I and j. But here Eij is a matrix unit. A matrix unit. It means it's a matrix with one on the Eij place. But Eij is a generator of the Lie algebra J-Len. Is J-Len Lie algebra generator. You see that we represent also generators of the Lie algebra J-Len by some matrices, but now it is important to make the difference, to distinguish them, because we consider Eij. We consider them as linear function on the dual space. Our linear function on J-Len star on the dual space. So when we consider the Lie-Poisson standard bracket, do remember on the symmetric algebra of J-Len, we identify it with polynomial functions on the dual space. So symmetric tensor algebra of the vector space J-Len. This is the field. I'm sorry, ring. The ring of polynomial functions on the dual space. JLN star. But of them are equipped with the Poisson bracket. Do you remember what is the Poisson bracket on this space? Yes, of course. The Poisson bracket of linear functions is just a commutator in the Lie algebra. But next, we extend this definition to all monomials by the Leibniz rule. And in such a way, we obtain the Poisson bracket on all this polynomial algebra. So, I have said this to describe that this element E is not a matrix in our case. It's a function. It's an element of the Poisson algebra. So that's why L is a matrix. Those L entries are functions on our phase space.
Like E, Ij, and E, Lk or something like that.
Yes. They play different roles. So these are matrices, but these are functions on the dual space. And for example, n equal 2. We get just a matrix 1, 2, E2, 1, E2, 2. So it's a matrix, and these matrix elements are functions from this Poisson algebra. If you consider n equal 3, okay, it's the same. Okay. I need some technical statement about such objects. About, in fact, some tensor calculations, which we will use.
So what we're trying to actually do right now is
we introduce the elements of the R matrix formalism to demonstrate that the spectral invariants in the Toda case are in involution. So it's a way to demonstrate that some integrals of motions are in involution, to demonstrate the Liouville integrability of the system. So first of all, I will need some tensor copies of the Lux operator. I introduce L1, which has the following form, which is the sum of ij, e ij, tensor product with 1 as a matrix multiplied by e ij. Maybe I will do some calculation in a more general case. I will introduce L by the sum Eij Lij, just describing the generic matrix element of the Lux operator L. So in our case, in the case of the JLN Lie algebra, this equals JLN case. So now I define some tensor copies of this Lux operator, which is described by the expressions 1 L1 ij and L2 are ij1 e ij Lij. So L is an element of the space of matrices multiplied, but in fact tensorly multiplied by the ring of coefficients of this matrix. In our case of GLN, it is multiplied by symmetric algebra of GLN. L1 and L2 are element of the square of the tensor square of this algebra of matrices n by n, tensor square, and tensorly multiplied by S of GLN. Is it approximatively clear?
The orientation of this one O times is, for L2y, it's one is in the opposite side.
I will propose to you some simple representation of object in this space. So you see, we can identify matrices. We can identify them with the of n square plus n square. Okay. And how we identify? We represent an element Eij multiplied by Ekl. This is from the first component and this from the second, as the following matrix, block matrix. So they take the if njth block of this matrix, and they take in this block an element with the indices k and l. Okay. Let me write it. Comment. We can identify n square or with by the following. Map Eij Ekl to this matrix. The KL matrix unit and the ijth n by n block, which is given by this picture. But the remark is that it is a homomorphism of algebras. So we preserve the multiplication. It's a homomorphism. It is a homomorphism of algebras. So it preserves multiplication. The multiplication.
So if I want to write like L3 or L4, how do I do it?
Sorry?
Can I write L3 also?
Yes, of course. But it will be in a bigger space, in the tensor third power of the space of matrices. We will use it, but for the moment we need such notations, and we need to work easily with them. So, have you understood the definition?
Yeah, for now.
But do you understand now this statement? It is not only some linear bijection. It is also a map which preserves the multiplication. We had the multiplication on the square on the tensor square of the space of matrices. Okay, we can then multiply matrix wise. But if we represent them by the bigger matrix, we have the multiplication on this space. So the statement says that this map preserves the multiplication. Okay, it's the home task. First home task. Home task 1. This to demonstrate this statement. Okay. We need this. And I'd like to write what is the example. What is the L1 and L2 in the simplest case of n equal to? N equal to, then L1 is the following one. So we take it is simple to write down what is L2. You see, we always take 1, which is the sum of EKK. And it means that we take the blocks on the diagonal of this matrix. So I'd like to write you this matrix. It is L, L, 0, 0. This is L2. Because you see, we take, these indices are the numbers of blocks in this matrix, in this big matrix. So it means that we take only the diagonal blocks, where the indices coincide, and then inside these blocks, we take the elements of the matrix L.
Elements of matrix L is the
Yeah.
matrix L?
Yeah. So it is E11, E12, E21, E22, E11, E12, E21, E22. This is L2.
Forward through matrix.
Okay. L1 is also simple, but not such simple. I will write it for you. So what we take? It is E11, E11, E12, E12, E21, E21, E22, E22. All the rest is 0.
How did you find the technical like this?
Please try to compare.
Okay, in this case it will also be a diagonal matrix and 1 Lij. So it means that
Yes.
what does it
Okay. So it's a sum of diagonal elements. But now you see this ij, it parameterizes the block. You see the ij element of our matrix L is put only in some elements of the block ij. So we see E11 is put only in the 1 block, but not on all places, only on places with equal secondary indices. We need also a very useful element P, the sum Eij, Eji, the sum over all I and j which is an element of the tensor n by n of the tensor square of the space of matrices n by n.
Like permutation operator?
Yeah, it's a permutation operator. Lemma. P acts on the pair of vectors as a permutation. How to do it? It's better to verify on the basis vectors in this tensor product. So if we apply P to EK tensorly multiplied by EM, then it is the sum of IJ, EIJ applied to EK tensorly multiplied by EJI applied to EM. So these are just the basis vectors in the vector space Rn, and they act as follows. Delta jk e I delta im ej.
So how did you get the second line?
This line?
No, the upper, here, from previous here. So you just
So it's a way how the tensor product of matrices acts on tensor product of vectors. It's act component wise. The first component acts on the first vector, and the second acts on the second.
okay.
And this is just the rule how matrix unit acts on the basis vector.
Yes.
So J should coincide with K, and if such, it is the image is EI. Okay. So it means that in the sum we should take I be equal to M and J be equal to K. That means I is equal to M and J is equal to K. And it is an inversion, just permutation of basis vectors, but it's a linear operation, so it acts as a permutation on all decomposable elements in the tensor square of our vector space, but it means that it acts on all vectors like this.
So you just proved it.
Yeah. So this is the permutation operator, and we need some properties of this permutation operator. Lemma. P L1 is equal L to P. But first of all, it is necessary.
To think that how L1 and L2 are connected.
Do you understand what is written? So you see L1 and L2 are matrices. So L1, L2 are matrices n by n, tensor square of the space of matrices, tensorly multiplied by our field of functions. I don't know, functions. It will depend on the model. But in our case, it is not important. P else is an element in the tensor square of the space of matrices, but it can be mapped to this space because we can consider them as matrices with constant coefficients. Okay, so they are in the same space. We can consider such an equation. And the proof is straightforward, but please try to follow attentively, because it's a matter of calculation of this type. So we have just to try to multiply. So there is an expression of the permutation operator iji, and we multiply by L1, which is the sum KL E KL 1 L KL, and we have to multiply them. We multiply them component-wise, so it's the sum over ij KL E ij E KL E ji. 1 is always 1, so we can skip this element. It is L KL. Then we multiply matrices in the first component as just as matrices. So it is equal ijkl e il delta jk e j I l k l. And this is equal. So what is k? Yes, for example, we can take k equal j in this formula. So it will be the sum of over I j l e I l e j I and l j l. Okay.
So this L is staying as an spectator. He is not changing anything.
No, it doesn't change. It is not changed because we multiply by matrix with constant coefficients, with constant functions. And the right part of this equation is the similar expression. So we need the sum of 1 eij sum ij kl e kl e lk lij, which is sum over ij kl e kl and the product of e ij e lk lij. And this is ijkl kl e ik delta gl lij. So here the element L is fixed by this delta function, so this is equal to e ijk e kl e ik and I'm sorry, L is equal J. Ik and L ij. Let us compare such expressions. So we need to change some variables, some indices to identify them, but the principle is the same, that these indices coincide. These indices are free, and they appear in the indices of the L operator in the opposite order. So you see these indices coincide, I. These indices are free, ji, and here you see ij. It is the same thing here. So if we identify this I, you see, it's the same expression.
But with different indices.
with different indices, but we can change indices, obviously. So this lemma is proved. We need some more lemmas which will be useful in calculations. I will write it as follows. Trace 1 with P, A1 and B2 is equal just AB.
It's like another property.
Yes, this is another lemma, but I need to describe what is written. So A is just a matrix, n by n, and B also. So A1 and B2 are constructed like this. So we place them in different tensor components. Now we multiply it by a matrix of permutation. And in this, so trace 1, it goes from matrices n by n tensor square to matrices n by n. And it is defined on matrix elements, on the tensor product of matrix elements as delta ij delta EKL. Is it clear? So in this space, this is a basis, and we define this linear map on basis elements.
Why do you need to put 1 here?
Because we take the trace over the first tensor component,
Okay.
and we get some element in matrices in the second multiply in this tensor product. Okay, but it will be very, very useful for us. So you see, now what is written? There are two matrices. They are placed in different tensor components, but they multiplied by permutation operator, and we take the trace over the first tensor part
Of the permutation.
of all this expression. You see, and we get just the multiplication of two matrices in the space of matrices.
Again, what is the index of matrix A and B? So A1 and B1 are
This index,
yes.
as
As the same.
like yeah.
And this AB matrix without index is that L? Without index.
Let me write it. So A is just a matrix, Aij. B is a matrix. There are two matrices. A1 is this one. Eij.
Okay. Now it's clear.
B2 is the sum 1 Eij Bij. Now we multiply them. We multiply in this space of matrices. Okay? So we multiply them, but we multiply them also by the operator of permutation. And in this triple product, we take the trace of the first component. So my statement is that the product is equal to the product of matrices. Let us do this calculation. So we just need to write all these expressions. So trace of the first component, this trace procedure, this trace map, and we write the permutation operator I, then the matrix A1, which is the sum, so Ij, A1 KL, EKL, tensor 1, and AKL, and the sum over TS, 1 ETS BTS. The trace, and we have to multiply all matrices, but it is not too complicated. KLTS EIJ multiplied by EKL. So in the first component we have only to multiply to these matrices, and in the second component only this. You see? EJI ETS. So we obtained the matrix in two tensor components, and its coefficients will be the product A KL BTS. Okay, now we have to simplify this multiplication. So it's a trace over the first component, IJKLTS. Here we have EIL delta JK multiplied by EJS delta ET. AKL BTS. Okay, now when we take the trace here, we introduce the delta function in IL here. You see? We introduce the delta function in I and L. So I'd like to write it in the following way. So it's a function over I, J, K, L, T, S with all delta functions. So delta IL, delta JK, delta IT, and this element became constant. We get only EJS multiplied by KL BTS. Okay, and what we get? We get the in this sum I is equal L equal T, these two deltas, and J is equal K. Okay, and it means that so we delete L and T and K in the summation. So we get a summation I JS, IJS. We get EJS, J I B I S. Okay, and this is just the product of A B. So on the gth S place we get this sum. It's an element of the it's a gth S element of this product. Please try to understand. Home task 2. Trace 1 of A1 B2P is BA.
Reverse.
It's a task just to repeat this calculation. Now we return to the L operator of the GLN, of the Lie algebra GLN. So it's some EIJ. And theorem. firstly the definition of notations. So it's an element of n by n square multiplied by our field of functions, or ring of functions. And this matrix part is defined as follows. So it has a pair of matrix indices, and this is a definition that it is the Poisson bracket of matrix element of the matrix L. So you see this matrix notation. It describes all Poisson bracket between all matrix elements of the Lax operator. Understand? So it's a general definition of this notation, but now I will formulate the theorem for this particular Lax operator, which describes the general Julian case. So in this case, L is equal to such a commutator. PL2. P is a transposition operator, and L2 is just L2 for this Lax operator.
Transposition or permutation operator?
Transposition, permutation. It's the same. But let's look at this expression. So on the left, we have the Poisson bracket of matrix elements. And on the right, we have some commutator of matrices. So we describe the Poisson structure in terms of some operational matrices. Okay, let us verify this. Let us calculate the left part. Lij KL, by definition, it is the Poisson bracket of Eij EKL, because the Ij element of the Lax operator is the generator of our algebra Julian. And we know that it is EIL delta JK minus EKJ delta IL. Okay. So this all this matrix, let me write it. L is the sum over IJKL EIJ EKL multiplied by this expression. Okay, and it means that, so it's the same as the following sum. In the first summand we can omit k, so we have to take k equal j. So IJL EIJ, and here k equal j EJL EIL. So it's the first summand minus, and here we can take L equal I, and it means that it is a sum over Ij and k, Eij multiplied by EKI. We take L equal I and multiplied by EKJ. So this is the description of the left part of our theorem. The right part also can be calculated straightforwardly. So we have Eij Ej, and its commutator with 1, the sum EKL, EKL commutator. So here the sum is over I and j, and here the sum is over k and l. And the first observation is that this one commute with its this matrix element, so it can be written in the following way: KL EIJ multiplied by the commutator J EKL EKL. And we know this commutator IJ IJKL EIJ EJL delta EK minus EKI delta LJ KL. And we also simplify this summation using the Kronecker delta functions. In the first summand we can take k equal I, so it is IJL EIJ EJL EIL. And in the second summation we can omit L, just substituting it by J, so it is the sum over I, J and K, E, I, J, E, K, I, E, K, J. Let us compare both parts. So the first part just coincide literally. And to compare the second part, they also coincide just literally. So it's the same. Okay?
Even the indices are the same.
Even the indices are same. Okay. So you see, the principal moral of this calculation that this long Poisson bracket in terms of generators is very concise in this form. Yes, so it's very controllable and concise, but it is also efficient to study the integrability properties. I'd like to demonstrate to you how to deduce the statement about the center of this Poisson structure on JLN. Do you remember what is the center of this algebra?
JLN?
Yeah. For the symmetric algebra of JLN, which is the Poisson algebra, what is its center? You remember we studied Casimir functions, symplectic leaves, etc. So we need to find the center. Reminder. The center of S JLN with this standard Poisson structure is given by traces of powers of the Lux iterator. We deduced such a statement by identifying the Hamiltonian vector fields on this space with the joint action of the Lie algebra. And so we we understood that the central elements should be invariant with respect to this adjoint action of the Lie algebra and consequently by the action of its Lie group. And evidently, such functions are invariant with respect to the conjugation by the group action on them. That's why they are central elements. But this formula allows to demonstrate it directly and very efficiently and in some generalizable way. So let us demonstrate the same thing using this formula. We have to calculate. Let us reproduce the statement from the formula 1. Let us reproduce this statement from 1. So the fashion of such calculation is very common, and it's one thing to understand along our course. So I have to calculate the following Poisson bracket. You see? And by the Leibniz rule, it can be expanded into the sum of from 0 to k minus 1 L1 power I L1 power k minus I minus 1. So there is a product here.
Yeah.
So I have to calculate this Poisson bracket of this element with each element in this product. So I take the element with the number I plus 1. I plus 1. And I calculate the Poisson bracket of this L with the L of number I plus 1. So this is the I plus 1th element in this product. And there is the rest in front and after. This element is given by our formula 1. So it's the sum L I and here P L2 L1 K minus 1 minus sum 1 minus 1 L1 E L2 P L1 K minus I minus 1. Now I have to calculate the trace of Lk with L. So it is also matrix notation, so it has indices. It is equal to the Poisson bracket of such functions. You see, it's a matrix here. But it is simple to understand that trace Lk with L, it is trace 1 of this tensor notation. That's why I have to apply my trace of the first component to this expression. So I need, in fact, to calculate this one. Trace to Lk L is equal the sum from k to L minus 1 trace 1 of L1 P L2 L1 minus 1 minus E from 0 to k minus 1 trace L1 E L2 P P L1 K is 1 minus 1. There is the same cyclic rule for the trace with respect to the first component if the matrix here lies only in the first component. You see, in this trace, I can put this element to the right. But L1, because it's a matrix in the first component, over which we take a trace, is equal to 1 to k minus 1, trace 1, p, L2, L1, k minus 1, because I multiply and the overall power is k minus 1, and minus from 0 to k minus 1, trace 1, and here I do the same. No, I make this one to this. Trace L1 power k minus 1, k minus 1, L2 p. But using the lemmas, the first lemma I proved, and the second lemma, which is your home task, it is the same as trace the sum I from 0 k minus 1. So you see there are p. This product is commutative. L2 and L1 commute in this place. So there is some matrix in the first component, some matrix in the second component, and the matrix p. So this trace is just the product of two matrices in one component.
So
L power k.
Just because yes.
Just L power k, and we sum it k times, and minus the sum to k minus 1, and here we have the same, not the same, we have p on the other side, but we have the same matrices here, so it is also lk, so it is 0 in all senses. Okay, we stop with the theoretical part now. We have a break for 15 minutes, and then we return to make exercises.